Thank you very much for this wonderful workshop. It's really one of the really good ones for me. So really great. So I will talk about stuff that I've been interested in for some time. Not mathematically very sophisticated, I would say, but a useful tool. So I'm trying to advertise a tool here that well, usually when you do some abstract version of a theory, it's not clear whether it actually will do work, right? And in this case, I think it does, and that's why I'm presenting it. So, in the finite to infinite dimension part, so of course there will be limits from finite to infinite, not so much the dimension. That's maybe not the most interesting part of it, but definitely it's a way to build limits. And as I said, it's an abstraction of things that I've been doing in various contexts. But just very useful. So one of the prime examples is this mean field limit that looks at permutation invariant many particle systems. And then there's the classical limit, also known as h bar going to 0. Then also the simple examples are also like the infinite volume limit of a lattice system, various continuum limits, so like renormalization group transformations, for example. Also, the repeated to continuous measurement that would probably tie in with what Martin had to say. I'll actually not say very much about this, but maybe anyway, there are many examples here. And so what can you hope to do at the general level, right? So the features of this inductive limit is, well, many times these limits are not just a limit where one parameter in the theory goes to some limiting value, but actually the structure of the theory. In these two cases, you get something abelian up level, and of course, well, it's not just a parameter going to infinity. The theory really changes, right? And so the kind of limit that we are doing is surprisingly a limit in operator norm, typically for states or for observables. And I'll say in which sense that is the case. And well, there's some general results that you can use a pattern in these different cases, and some of the stupid work that you have to do otherwise would have to do every time can be done once and for all. And I think that's a useful thing to know, even if it's not really very complicated. So first of all, what should the limit space be? That is one of the questions. Then how do we extend dynamics? So that will be the largest part of the talk. Actually, we started with equilibrium states and made a limit of equilibrium states. And in all these cases, there's stuff you can say at this very general level. And then in each concrete situation, it's pretty clear what you then have to show, but a lot of the bookkeeping stuff is out of the way, right? So that is the idea. Okay, so I call these soft inductive limits. And so typically in these situations, there's a limit parameter, and really like every finite instance in that sequence of systems, will sort of be a different universe by itself. You can't add operators between different universes, something like that. So then it's a question, how can you even call them similar? In what sense could there be a limit, right? So you have, like, let's say in the mean field limit, there's n particle systems, and n is different for all these systems. So how can you compare a 7 particle and a 15 particle system, right? So you have to say something there. And that is the basic approach. You have to we'll introduce, so the conceptual basis for any such limit will be exactly this idea of comparison. How can you compare operators in these different spaces? And we'll do this in a very simplistic way, namely introducing maps that map one space into the other, and then we can make a norm comparison. So here's how the scheme works. So the indices will be typically, well, you could think of the natural numbers, but actually in many situations it's better to have a general directed set. For example, when you take an infinite volume limit, then you're taking a limit over all finite volumes. Or if you take the continuum limit for continuous measurement, you have a partition of your time interval. For each partition, you get some kind of a CP map and a dilation for that. And then as you refine the partition, you get a limit, right? And stuff like that. So it's in many cases, you could index then the partition or the finite set and make a limit over a sequence, but that's actually artificial. So in many of the situations, it's natural to think of this as a general directed set, therefore net. Not so much because of metrizability issues. So, right? So let's take so for each n, therefore En would be some Banach space. A norm space actually is good enough. We don't really need this to be complete in many cases. What else? Now come the comparison maps, right? So they take you. So the directed set means there's a meaning to one index being larger than another, containment of finite sets, for example. And then there is an injection, there's a map that takes you from the space with a smaller index to the one with a larger index. We want these to be linear and contractions, and the key property is something like transitivity of the comparison. So it should make sense as a comparison. And therefore we want a limit like, so this compares a single step embedding to a two-step embedding. And with this particular order of limits, you take the lim sup of these guys for the largest index going to infinity, and then the limit of the second index. M is fixed in this equation. And it's in the strong sense that it's applied to an element, right? It's not in the norm. Of course, this could be true. For example, this could be identically zero. In many cases it is. Then it's an inductive limit of the usual form. But we allow these norm errors somehow. And so it only has to be asymptotically transitive, not strictly. Okay, so this is a pattern really. So for example, you don't need Banach. Actually, you could do this on any metric space, but very often you go the other direction. There's more structure. So for example, these would be order unit spaces, and the maps are positive, or they are operator systems and they're completely positive. The normalization could be put in, or if you're a C-star algebraist, you might want homomorphism sometimes, right? For example, the inductive limit for the infinite volume system of a spin system, there you have homomorphisms that do the embeddings, which means that automatically your limit thing will be, limit space will be null. But that depends, right? So it's very easy to take this pattern and add structure as needed. I'm not going to do this in every, I mean, not making a big issue out of that. So here's the key notion. So we have this comparison. So now we can compare elements in different spaces through this comparison map. And therefore we can say that XM sort of is like XN, right? Relative to this inductive system of comparison maps. And so we say that a sequence or a net where each element actually lives in another space is convergent when this Cauchy-like condition is satisfied. So when both indices become large, this goes to zero. So there's some subtleties of how to set this up exactly, but this is basically a Cauchy-like condition.
So this is for every fixed M.
This is for a sorry. N. This case should be
M, I guess. Should be M,
this
yes.
case should be M. I'm sorry. Okay, so these are the convergent things. So now, what does it mean? To what do they converge? Right? So a simple way to say that is to say when they converge to the same thing. And that, by definition, just means that the norm difference of the two sequences goes to zero. So we have convergent sequences, we have null sequences, where the limit of the norms is simply zero, limit of numbers, right? And these are obviously also convergent because you can just use the triangle inequality there. The J's are fractions, so you can directly have a null sequence are convergent. So we can simply take the quotient space of the convergent sequence mod null sequences, right? So this is just saying that we know that these two should correspond to the same, and that is the sense in which this is a limit in norm, right? So norm small perturbations of a sequence don't change the limit. And this quotient would be something like the abstract limit space, right? So we know how to build the limit space, but of course I call it the abstract limit space as a bit of a disclaimer, because that is not, often this is not the useful part of it. You want a concrete representation of what the limit space is like. You want that to be simpler, actually, in many cases than the EN. So in mean field problems, working with finite n, you basically have a generic quantum system, horribly complicated, but in the limit, it all becomes simple. So that's maybe about for yesterday's discussion. Right? So, so this is the limit space. And there's this is some of the bookkeeping, basic bookkeeping stuff that is very easily done. So first of all, well, this is not completely trivial, but you can see that the limit space that is defined like that is a Banach space, even if the ENs you don't care. But this limit space is actually complete, and the norm is, you get the norm actually as a limit of the norms, right? Or the superior limit. Then there's actually the asymptotic transitivity directly can be translated as saying that sequences like this that you get from mapping up from a fixed element, that these would be convergent, right? And so so then there's an injection or a map from each of the finite spaces to the limit space that just takes the limit of the sequence. And again, by definition, these basic nets are dense. So you can think of the simple nets that you get just by up symmetrization or upwards mapping, so to speak. Okay, some general remarks. So first of all, this notion of convergent nets is more fundamental than the comparison maps themselves. The comparison maps you don't really care about. You could change them at any finite index without changing the limit setup, really. So only their asymptotic properties are relevant, right? So, and therefore, so you could say that two inductive systems are equivalent when they have the same convergent sequences. And you could express that directly as a similar kind of strong norm bound. But really the important concept are the convergent nets, right? Yes, so this whole construction is, you could think of this as a joint generalization of two things that you're doing all the time anyway. One is strict inductive limits. So those are the ones where you have equality in this transitivity. And this is in many cases, you just write down a strict inductive systems. For example, infinite volume limit. And anyway, so that happens a lot. And the other one is the completion construction. Each EN is a Banach space, well, they actually maybe all the same. And these maps are just the identity. There's not much to compare here. This part of the story doesn't have to be told, right? But going to the convergent sequences, that is the Cauchy sequences, and identifying that mod null sequences is very well known, very well known to everybody. So the completion construction and the inductive limit construction is sort of built into, put here into one. You could actually do this in two stages. This is sometimes done, right? So you take the strictly local element of the quasi-local algebras by just taking the strict inductive limit. What you get is then not a complete space. So you complete that and get from the local algebra to the quasi-local algebra. You do that in two steps, right? But I think that's actually much nicer to do it in a single step than I did it here. Yeah.
Does every subinductive limit lie split in
well, we don't have an explicit example of a limit that is not equivalent to a strict one. So in some cases, it's an open problem, whether it is actually strict or not, or equivalent to a strict one, right? Of course, you can write it in a way that it's not strict, but can you, the interesting question is, can you make every soft inductive limit equivalent to a strict one? That I actually don't know. So here's another way to do that. We are talking about comparison between different finite indices, n and m. but you could also compare directly with a limit. And that would be like, you would maybe call that an approximation scheme for the space E infinity. So En is somehow close to E infinity when you have an injection and a projection that will be the identity on the smaller system, but converted strongly to the identity on the E infinity. That's also very, very common construction. And in that case, you can just build one of these soft inductive systems by injecting with one index and projecting with the other. And then you could just check that this strong convergence gives you this asymptotic transitivity. This is just saying that you can build, sometimes you can build things directly on the comparison between finite values and the limit. And I'm not, well, okay. So actually, a split and a strict inductive limit are usually not the same. So so you can have, so for example, the classical limit can be made strict. It can also be written in a split way, but then it's not strict. So it's a matter of taste what you want, or which kind of technicalities you want to avoid by setting your limit, choosing one of these properties. Okay, so let me just go through the examples and how that plays out there. So in the mean field case, you have a many particle system. So A tensor n is your observable algebra, and I'm doing this for unobservables, right? So it could be a finite dimensional matrix algebra. Like when you talk about spin systems, that's typically what you mean, but that's by no means necessary. So what do you do? In order to embed as an observable for a smaller system into a larger album, you tensor with the identities, as you do in the quasi-local algebra, but then you symmetrize over all permutations of these n sites. So if you take a one-site operator and you average, then you have like 1 over n, like all its shifts. You have n terms. If you do this for a two-particle operator, you get 1 over n times n minus 1 times all possible ways of injecting it at two places, which is, if you multiply this by n to make it extensive, it's exactly a mean field interaction in the usual sense, right? So the realization behind that with Guido Raggio and myself in Dublin Times was that you could think of this particular kind of averaging of two-particle terms as installing this kind of permutation symmetry. Right? So permutation symmetry is really the key to mean field systems. So it is a strict system because if you average again, if you embed that into a larger system and then average again, the smaller permutation group gets absorbed in the larger one. So it's clearly strict. But it's actually unknown whether this is strict. Unknown to me, that is. There's in the classical case, functions on an interval, there's something called Bernstein polynomials, which are related to maybe making it split, but I don't know whether this can be done. So this is, for the time being, this is just on the observables. Okay, so now a very simple observation is, if you look at basic sequences in particular, that is, you start from a finite value, some finitely localized thing, and then you do the symmetrization game. And you have two such sequences, and n becomes large. Then the averaging means that you're embedding onto different sets of sites, and they typically don't have an overlap. So so then you see that the n-wise product will typically also be convergent up to 1 over n errors, basically. And also that the commutator, because they typically end up in disjoint sets of sites, they commute. So the limit is an abelian-Cista algebra. So so although this is clearly not a homomorphism, asymptotically it is, and that is extremely useful. So then what are the states? Well, so this is the same. Now on an abelian-Cista algebra, you look for the Gerfan spectrum. That is, you look for the multiplicative functionals, and they're easy to see here. Well, if you just evaluate on a homogeneous product state, this gets absorbed under the symmetrization. So you directly get a Cauchy sequence for the expectation values, a convergent sequence. So so actually, this identifies the pure states of the that is the Gelfand spectrum of this abelian C-star algebra. And therefore you have an isomorphism of the limit space with the continuous functions on the state space of this one-side algebra A. What I just showed to you is basically the Definetti theorem. Yeah. So because if you take a general state on that E infinity, and it's clear that every permutation invariant state on the infinite tensor product would give you such a state, then you take the disintegration of that state into pure states, and that is your Definetti measure that tells you it's actually an integral over such homogeneous product states. Right? So this is the Definetti theorem. Okay, classical limit. How do you do that? Well, then at each, so now I do write the index at h bar. It doesn't go to infinity, but goes to 0 in some way. And so we have a system of while operators where there's a fixed phase space, let's say, with a symplectic form here, right? Finite dimensional vector space with a symplectic form. And so the Hilbert space for the finite system, or for a system with finite h bar, is Weil relations, and they're the shifts, and the shifts play a special role because there are two norm limits that we can do, one for the states and one for the observables. Right? Now for the states, we just take the trace class, and the J system will be, the key property is that it will be commute with the shifts, although the shifts on phase space are implemented with different h bars. We can still talk about the shift of the phase space. Right? So only the phases will be different. And so they will be covariant for the translations. One way to say it is that these scaled down while operators should be convergent. So it's enough to give a broad characterization of this J. I could write down an explicit choice, but using coherent states, for example. And so this can be either made split or by choosing these J's properly or strict, all goes together. Now, on the observable side, B of H is a rather large object, and the norm convergence cannot be shown for that. So instead, we take the strongly continuous elements under these translations. So that on phase space, this would be, well, actually, I didn't tell you the limit spaces yet. The limit spaces in this case will be L1. On phase space, in this case, it will be the uniformly continuous subalgebra of L infinity on phase space. Right? So you get the function out. These embeddings into the limit will be given by expectation, taking expectations with a coherent vector of CV functions, whatever you call that. And also this one is asymptotically homomorphic. So even though the J's at between finite values of h bar, well, there's a change of the symplectic form here, so there couldn't be homomorphisms. Right? You're changing the algebraic structure, but asymptotically that's true. So if you're close to the limit, it doesn't matter much. Right? So you nearly have a homomorphism, and that also is a very powerful tool. Okay, so that's the classical limit. Then, then also we have a limit, a norm limit for the states, a norm limit of the observables. So you can ask about what happens to expectations. Now, in general, when you have a norm limit on the observables, you have a J star convergence for the states, right? So a sequence of states is J star convergent is of a J convergent sequence or net of observables. It produces a convergent sequence of expectation values. The limit is then a functional on the limit space. So every norm convergence has a weak convergence associated with it. And that these two match up, that is, if you have convergence of the states and of the operators, that then the expectation values converge, means that the norm convergence, norm convergence implies the weak convergence. Another way of saying. So these two kind of limits match up.
Do you really need to consider finite dimensional phase space? Yeah.
Yeah, so this is infinite dimensional phase space. I mean, the phase space is finite dimensional. The Hilbert space, of course, is infinite dimensional. We also had the finite dimensional Hilbert spaces at some point. That's another story. Yeah, so in infinite dimension, this is you could do things like that, but I guess it's a bit messy. So then quasi-local algebra is just what you know. This is in Bertelli-Robinson inductive limits as usual, right? And the quasi-local algebra is the limit space. I want to make some comments about that. This is why I included. And there are many more examples that you can make. For example, this limits taking you from finite Weyl systems. These obviously infinite dimensional realizations of PQ for commutation relations. Continuous measurement, I had I known your talk before, I would maybe have included more of that, because you can make a nice inductive limit out of finite interval dilations, and how to put them together in an inductive limit construction to get the state upstairs. So all the integration with bosonic Fock spaces can be taken out of that. Also, sometimes it's, I mean, if these J's are completely positive, as you should do when you can, right? Then you can also very easily tensor these inductive systems. So if you have like combined systems of a spin system with something of which you take the classical limit, you just put that together and it's done. No extra work. Okay, so let's talk about dynamics. So dynamics. One thing to realize is that the Hamiltonians are typically not convergent. So in the mean field case, the mean field convergent observables should be thought of as intensive quantities. They're averaged quantities. Whereas the Hamiltonian should be extensive, so it should have a factor n. But that is actually the definition of a mean field Hamiltonian system. Also in the classical case, so there. This could be a convergent object, the Hamiltonian, but we always divide that by h bar. So you could say there is a factor h bar between the notion of an observable and the notion of a generator. We do that normally by just putting the h bar in the exponent like this, right? But these are really very different concepts, and these implementing unitaries, they must not be convergent because we have a product theorem. And then they would just factor out the commutes in the limit, right? So in the limit we get a commutative system. So if they were convergent, you wouldn't see any dynamics in the limit. So anything that any set of unitaries that implement something in the limit cannot themselves be convergent elements, right? So you have to look at what they implement, and that makes sense. Yeah, and also in the lattice case, it's clear that the Hamiltonian is never a quasi-local element, right? So so typically Hamiltonians are not themselves in this class. What you get in the mean field in the classical case, that is if you go to the next order, that is in the mean field case, you multiply a commutator that by itself would go to 0. If you multiply that by n, it produces exactly the Poisson bracket that you need. I'll give that in more detail. The same is also true in the classical. So the key thing that you would try to show in all these cases, well, you would have a semigroup of operators on the observables or states at finite level, and you want to take that to the limit. So what you have to show is that if you have a convergent sequence, the n-wise application of your standard time evolution produces something that is also convergent, and then you can just take the limit of these sequences, and that defines your limiting evolution. So that's the general pattern here, and the question is how can we set this up? So the theory that we have for this, well, there are two aspects here. One is you want the limit for the generator, or that is the limit on the equations of motion, but you also may want the limit of the semigroup, that is the limit of the solutions, right? So those are two slightly different things, but of course one is helpful for the other. So actually everything here is just a nettified version of semigroup theory. That is, instead of working on a Banach space, you work on the sequence space in some sense, right? So then for this, when you have a densely defined generator G, and we know that S minus G has dense range if you apply to its domain, right? then this condition says that it actually generates a semigroup. This is only says that defines the generator in the limit, or a prospective generator, one that might become a semigroup. And this way of proceeding separates, on the one hand, the net structure mostly does A. That is, you show that the generators produce sufficiently many convergent sequences so that you can define the generator in the limit. But then you have the structure of the limit space, and there you have to show that something like this, that it actually satisfies the generation condition. And so that is how we will work. So most of the, so yeah, sometimes the second part is completely easy because you know the dynamics in the limit space. If that is a Hamiltonian flow, you don't have to think much how to show that it generates. So here's the basic theorem. So we have these semigroups at every finite level. They have a generators Gn, and now this is what we want to show, right? So that the finite level, if we apply that at every n to a convergent sequence, then we get a convergent sequence, which means that we have a semigroup in the limit, right? Because these things obviously multiply, and that will have a generator, right? Now you can also look at the finite level resolvents, and they would have, if you want a similar property for them, but then you also need that the infinite volume resolvent, or the limit of the resolvents, has dense range, which is the condition that you can find a dense domain on which this is actually the result. Or there is a set of this is technically how you would do it most of the time. You choose a convenient set of convergent nets on which you can compute the generator nicely and control it. And that defines the G infinity, basically, right? So actually the definition of G infinity, if you want to do it directly, would be you define it on all sequences, convergent sequences, so that Gn applied to this element n-wise is also convergent. That is the domain of the sequence of generators. And if that is well defined and generates a semigroup, you're done. And this second part is controlled by looking at the closure of such a space. Okay, so how does this work in the examples? So in the mean field case, this is how in the Hamiltonian case, this is how you get you have a limit for the energy densities. That is an intensive variable. And that means that you get a Poisson bracket. I didn't define the Poisson bracket for you, but that gives you directly a Hamiltonian flow on the one particle state space, right? That was your Gelfand spectrum. So how do you define this Poisson bracket? That has to be done without reference to this whole limit. You just have to say directly what it is. Well, how does a Poisson bracket work? You take the gradients of the function and you do a certain bilinear combination of that. Now here's the gradient. A gradient is defined by a directional derivative and along the state space in this case. So these are states, right? So it is evaluated at the point sigma. That's the point where we take the derivative, and rho characterizes the direction, right? And so we can go in the linear direction, take the derivative, and that is a linear function in rho. So that defines a gradient. And the Poisson bracket then simply takes these gradients, takes the commutator, and takes the expectation at this point. This is what actually comes out when you look at the next order of the commutators, right? So the leading order for the commutators is the single site overlap configurations, and they average to something like that, right? So you can read this, but this symplectic structure it's not a symplectic structure because it's degenerate, right? But this Poisson structure actually has the property that the time evolution, the flow that you get from that, the Hamiltonian flow that you get from that, automatically preserves the spectrum. So you stay it's locally, you have just a unitary turning state, but it depends on the state, what the unitary is. Actually, this is very well brought out by this idea of tag dynamics. So we take this kind of dynamics, mean field dynamics, but in our construction of the inductive system, we just leave out some sites, some fixed set of sites. Actually, that could also be growing, but that's a technicality. Let's take a fixed set of sites that we do not symmetrize over. And I call those the tag particles. We keep a special eye on them. And so then the limit space, this is actually a tensor product of the inductive limit I showed you with an identical one, with a trivial one, right? And then it's clear that what you get is a tensor product of the limit spaces, which is, this is the constant space, and this is the limit space that we had before, right? So this is just tensoring inductive systems. And if you take it for the Hamiltonian dynamics, this will actually be unitary on the, so that you can think of these as the A tensor M valued functions on the one particle state space. So this is the flow on one hand, right? But the tag particles just undergo unitary evolution with a time-dependent Hamiltonian. And this gradient is taken at the appropriate point in the bulk is exactly the time, the Hamiltonian. In other words, the bulk dynamics acts like an external field on the local dynamics. Right? You have to follow the bulk dynamics. That gives this dependence. And then you just have the local Hamiltonian for the tag particles.
So can one understand this, that one looks at these, actually the dynamics of these M sites as created by the effective Hamiltonian of the rest?
So the tagged sites have the same dynamics as the other sites. It's only that I'm looking at a part of them to sort of get a closer look at what happens inside the mean field system. Right. So but the dynamics is just symmetrized over everything. So this is this. So in particular, if you take the state itself, it will just move under this dynamics. The state sigma, then would just if you're on the bulk state, then it would just move. I'll say more about that. So here's the Lindblad case. Now, one way to do that is you take a Lindblad generator on finitely many sites and you symmetrize, but now with a different symmetrization operators, namely you symmetrize as these operators should be symmetrized, and you scale with an n. And the simple case of that is that you take a Lindblad form, and just the jump operators are themselves convergent sequences, and the whole thing is scaled with a factor n. So this you can clearly do, and for this you can directly write down the limit, because you know what n times a commutator goes to, which is I times a Poisson bracket. Right? So but also in this case you show generally that you get the tag particles move independently. And this is some kind of CP co-cycle for this evolution. So the whole thing has to be a semi-loop, of course. And the flow now can be basically an arbitrary flow on the one particle state space. So you can get, we show that you can like you can implement a dense set of vector fields in this way. Right? Now, if you take the special form, then actually the spectrum will be conserved. And actually there is a local Hamiltonian. So it can happen that the bulk dynamics is dissipative and the local dynamics is Hamiltonian, but it can also happen that the bulk dynamics is maybe Hamiltonian and the local dynamics is contractive, because this is a trivial remark. This bulk dynamics always drives towards the bulk state. And if you include in the jump operator here some permutation, this will exactly happen. That is, correlations between the tag particles will be created. So if you allow them by your Lindblad form, allow the particles to talk to each other in another way, for example, by a permutation, that will not change the bulk dynamics because you're symmetrizing over permutations anyway. But it will change how the local particles do their exchange correlations. And so this could be driving to equilibrium, so be very strongly dissipative, but the flow is trivial. That is when you take only permutations here. But you could also have like the dissipative thing here and the local dynamics is. So you get all kinds of possibilities depending on the scale. I have to speed up. Classical limit.
I have one question, but would this imply that should you have now generator that is of Lindblad form at any time? At any time, but barring from.
Oh, yeah, that's also the same theory.
Okay,
So the, I mean, but then you would need that, I mean, there's a particular scaling with N. There's worse scaling, actually, the diffusions that were talked about just a little while ago by you, also go in here. If you square the generator of an automorphism group, you basically get the generator of the Gaussian sampled evolution. And you can do this goes through the limit directly. So you have generators that scale with n squared and would make a diffusion on the section. Here you still have a flow, right? With the scaling in n, you still have a flow, but you could easily have a diffusion. Same goes for the classical. So 2 minutes, right?
Is the tensor symmetrized, or if you look at your AJNs, are there page before, is this tensor symmetrized, or?
Well, you symmetrize, you know how to symmetrize an operator, and you apply that to an operator, apply the Lindblad, and then permute back. So okay, so classical limit, actually, so this is the only way to do the classical limit. So if, for example, it involves some of the typical artifacts, if you look at WKB methods, then you look at such wave functions, they are actually J-star convergent states in our scheme, and they produce measures on phase space. They're not norm convergent because this is not an L1 density, but they are weakly convergent, and they converge to something supported on such a manifold where the momentum is a gradient of this action function. Now, if you apply the dynamics to that, this picture, for example, an oscillator, then this whole picture would turn in phase space. And this fact that this line is always like a function of Q, that will be wrong. So you get caustics. And a lot of the semi-classical theory is about Maslov indices and all this stuff where you really have to discuss these caustics in detail. We don't have to do that. It's automatically clear that you have the flow there. And this picture will turn in phase space. It's stupid to look at this as a function of position. So this form is not stable under the flow. So 2 minutes, you said, right? I thought I had not enough material. Anyway. So here's one thing that you should do, right? Classical limit does not just mean that the expectation values have a certain form. It means that you could look as often as you want and you don't really disturb the system. So you can make a limit of monitored processes, and you can have mild measurements where mildness depends on h bar in some sense. Right? And you could either do this as fixed times or have jump events in Lindblad evolution as in Gerade Rimini Weber. Right? And then if you do these, if you scale these measurements right, then what you get in the limit is the same Hamiltonian dynamics, but at the same time, the monitoring process converges to its faithful image of your trajectories. So that is what the classical limit really should be. Quasi-free, this is stuff that I did with Alberto Bacchielli. Let me just, yeah, maybe, okay. Maybe these just these comments. So why did I come up with the lattice dynamics at all? Because it shows some of the features of these limits that will be useful in other cases. So one is that, for example, look at the translations in a lattice. None of the finite volume systems have translation invariants. Now you can work around that by making artificial shapes of your finite volumes and have periodic boundary conditions, which is physically extremely silly, right? Of course, we know why people do that. I mean, you want the group back, right? But in the limit, getting the group back in the limit in these schemes is automatic because the basic sequences that start from some finite volume and then are symmetrized up, if you shift that thing, it still is one of those basic sequences. So on the level of sequences, there's no problem. And immediately, it's clear that how the translations act. You don't have to do any work there, right? The same goes for boundary conditions. So if you look at the standard picture of boundary conditions in lattice systems, what people write down is like open boundary conditions. You have a certain number of terms, and then you take only the terms that live in your volume and so on. Or maybe you artificially make periodic boundary conditions, but it's not really clear to what extent the boundary conditions play a role. In this scheme, it's extremely clear that they play no role whatsoever. So you can, even if you do periodic boundary conditions and let the system come back from the right when they left on the left, this is one of the conditions in our basic dynamics theorem. So your set of dense nets would be one that doesn't even see the boundary. What you have to take care of is that it remains dense. So that is that you really exhaust everything, but you have to do this only in the limit. So this space D could be one that doesn't even see the boundary conditions for the generator. And then you just apply the theorem and you see that the limit is simply independent of the boundary condition, as it should be, right? It's not a big deal. And if you use Bertelli-Robinson-like techniques, you could probably twist that onto that setup. But in this separation, it's clear that already the generator at the infinite volume limit doesn't see that. And then you have the same kind of work to do that this actually generates, right? So this is, the independence of boundary conditions is something that works extremely naturally. Right? Okay, I'm not talking about equilibrium states. That's actually how we started. Convergence of partition functions. So thank you very much for your attention. Sorry for going slightly over time.